Hi everybody, this is lecture 15 and today I'll wrap up our discussion of conservative vector fields and then introduce you to Green's theorem, which is the next big theorem in this class, one of those theorems that tells us what happens when we integrate a derivative. Okay, so here's where we stopped. We were talking about when a vector field is the gradient of a function. So for example, here are two examples. So if in the first case we have the vector field y comma x, that vector field happens to be the gradient of a function. It's the gradient of the function x times y, right? If I take the gradient of x times y, the x partial is y, the y partial is x. So that's the given vector field. But on the other hand, it turns out that if I just put a minus sign in there, just change the vector field a little bit by that minus sign, then the vector field is no longer the gradient of any function. It's not the gradient of x times y, and it's not the gradient of any other function. And the way I know this is by this arcane looking method. Right, so here's what I'm going to do. I'm going to call the first component P, the second one Q. I mean, the names are not important, but it's what I always do. So I'm going to look at the x partial of the second component. So in this case, that's 1. And I'm going to look at the y partial of the first component. So that's P sub y here. That's -1. And then you see that these two are different. Right, and it's because they are different that I know that f is not the gradient of any function. Let me explain why. Right, so let's look at this test for gradient vector fields. Okay, so let's say that our vector field f with general components p and q, these are functions of x and y. So if this vector field is the gradient of a function, then this means that p is the x partial of the function, right? And this is my notation for df dx, and q is the y partial of the function. And so let's look at the x partial of q. So the x partial of q is so the x partial of q is the x partial of the y partial. That's f y. That q is f sub y. So q sub x is f y x. Right. We're taking the x partial of the y partial of f. On the other hand, p sub y, the y partial of the first component of the vector field, is the y partial of the x partial of the function. So that's the second order derivative. And then it turns out that for all ordinary functions, functions whose derivatives whose partial derivatives exist at all points and whose partials and where these partial derivatives are continuous. So for all ordinary functions, if I take partials in the order first with respect to y, then with respect to x, that's the same as taking the partials in the other order. So this equal sign holds for all ordinary functions, right? Because this part is equal to this part. Actually, let me just organize this in a way that makes in a better way. So here's what I'm using. That have this equality for partials. You can take any for ordinary functions. They can take partials in any order, and the result is the same. So this is true, and therefore, if this tells me that if a vector field is a gradient of a function, then the x partial of the vector field of the second component of that vector field must be equal to the y partial of the first one. Cool. So this is a condition that must be satisfied if the vector field, if f, the vector field capital F, is the gradient of some function, right? Q sub x must be equal to P sub y. Now, But then you could ask me, okay, suppose I give you a vector field. So let's look at the first example again, right? In the first example, if I take in the first example, if I take the x partial of the second component, I get 1. And if I take the y partial of the first component, I get 1 as well, right? So q sub x is equal to p sub y in this example. But let's say I still hadn't found a primitive. I still hadn't found a potential function. Is it true? So could I conclude just from the fact that q sub x is equal to p sub y in this example that there exists some solution to this equation? That there exists some potential, maybe which I'm unable to find right now, but can I be sure that there at least exists one? And the answer is not always. So in this example you can, because this vector field satisfies that q sub x is equal to p sub y, and another extra condition, namely it's defined for, so these formulas here are defined for at all points in the plane. There's no division by 1 over, there's no division by 0 or anything. But in general, if I give you a vector field that is maybe not defined at the origin or something like that, then q sub x being equal to p sub y would not guarantee that the vector field is the gradient of the function. But in any case, I'll just state here that, but in the easier, more very common situation that the vector field is the vector field that we're asking, is it a gradient? In the case that vector field is defined for all points in the plane, meaning that the formulas for the components make sense for all x and y, right? And they give you ordinary smooth functions, differentiable functions of x and y. If the vector field makes sense at all points in the plane, then this test goes both ways. I can detect whether a vector field it's an if and only if condition. I can detect whether the vector field f is the gradient by testing this. So if it's equal, then it's a gradient. If it's different, then it's not a gradient. Okay, so let me state the test so you can all refer to it later. So if f is defined at all points, at every point of the plane, so this means that the two component functions p and q are defined for all inputs for all points in the plane. So there's no division by 0 or anything. There's no log of a negative number or something like that. So in this situation, and furthermore, and I know that q sub x is equal to p sub y, then the vector field f is the gradient of some function of x and y. Right, I still have to get into how we find this function. I'll show you this, I'll show you the method in a moment. But this theorem is telling me that this condition, I can always use this condition, q sub x equal to p sub y, to disprove, to show that something is not the gradient of a function, like here. So down here, I just checked that the two partials were different, and then I was able to conclude that f is not the gradient of any function in this case. So this I can always do, but it turns out that if the vector field is defined at every point in the plane, then I can use this condition to prove the vector field is a gradient field, right? So let's see that happening. Okay. So here's a homework problem. It has appeared in exams in the past. So example, we're given a vector field. So we want to find, I'm going to give you a family of vector fields that depend on a parameter a, and we want to find the value of the parameter that makes the vector field the gradient field, right? So we want to find the parameter A so that the vector field, so here's the vector field. First component is 4x squared plus axy. So this is that parameter a times xy. And the second component is 3y squared plus 4x squared. Okay, so find A so that this vector field is a gradient field. So that's our job. So here's how we do this. Let's take the partials, the x partial of the second component. Let me call that second component q, as I normally do, and the y partial of the first component, let's call it p, as I usually do as well. So q sub x in this case is the x partial of q in this case is just 8x. Okay, and the y partial of p in this case is let's see, it's a times y. So you see, for these two partial derivatives to be the same function of x and y, I need, there's only one value of a that makes that happen, namely a must be 8. So there you go. So next, so now we know, so for this value of a, so from now on, a is going to be 8, right? We know, so with this value of a, I know for a fact that this vector field is the gradient of some function. So what I want to show you next is how we find that function. So let's find the potential function. Let me do it up here. Right, so we want, so from now on, a is equal to 8, and this tells me that the vector field f is the gradient of some function. Right, let's find that function. So we know, so this equation has two components, right? This equation between vector fields is just saying that the first component of f is equal to the first component of the gradient of little f. So this is saying that the gradient, so here we have two equations. First one says, so the first component of the gradient is the x partial. This is equal to the first component of f, that's p, so 4x squared plus 8xy. And this equation is always also telling me that the y component of the, so the second component of the gradient, f sub y, is equal to the second component of f, that's 3y squared plus 4x squared. Okay, so I have these two equations, and I'm going to use them to figure out what this function f is. And I'm going to give you a procedure that works every single time. Assuming that the vector field is defined at all points in the plane, and that the x partial of q is equal to the y partial of p. Okay, here's that procedure. I'm going to take equation number 1, right? So equation number 1 tells me something about the x partial. That's something I get by fixing y and differentiating with respect to x, right? I'm going to take the first equation, and I'm going to integrate the first equation. I'm going to fix a y coordinate. So for each fixed value of the y coordinate, I'm going to integrate both sides with respect to x. So I'm going to fix y and integrate with respect to x. This is going to tell me that the function f is so the integral of the right hand side with respect to with respect to x. So that's 4/3 of x cubed, right? The integral of x squared is let me just do it as I usually do. 4 times x cubed over 3 plus the integral of 8x with respect to x, that's 4x squared times y. And here comes the interesting bit, plus a constant. But here's the thing. We fixed, when we did so we originally had functions of 2 variables on both sides. F depends on x and y. So we had functions of 2 variables. I fixed one of the variables, y. So when I fix that, I get both the 2 sides were, I mean, I still had a dependency on a single variable, and then I integrated those functions of a single variable to get this. But now the issue is that the constant I get can depend on the value of y I fixed, right? So different values of y can give me different constants. So and it's important to think about that. So this constant c is really a function of y. Okay. So notice this, that the content, like the content of equation 1 is the same as the content of this other equation. If I differentiate, so I was able to deduce this equation here from 1, but I'm also able to deduce 1 from this equation. If I just take this equation and take an x partial of it, I'm going to get exactly equation number 1, right? So if I want to maintain the same amount of information, I have to include this dependency here. The fact that this constant can depend on y. Okay, so next up, I want to use, so this is me using equation number 1. Next, I want to use equation number 2 to find this potential function, to understand this potential function f. Let me note that we already made some progress. We know how f depends on x. All that remains is to understand how f depends on y. So I just need to understand this function c. We did make some progress. Here's how we're going to understand c. We're going to use equation number 2. So to use equation number 2, I'm going to take a y partial of the work of what I already know, right? Because the equation number 2 involves a y partial. So let me just take a y partial. This is going to tell me that the y partial of f is equal to, so the first part gives me nothing, so 0. And then the y partial of the second term is 4x squared, and the y partial of the third component, the third term, is just c prime times y, right? See the derivative of c with respect to y. Okay, now if I compare this with equation number 2, so if I compare what I got over here with equation number 2, I get that c prime, so we have 4x squared on both sides, and so this means that c prime of y must be equal to 3y squared, right? So c prime y, the derivative of c with respect to y, is 3y squared, and therefore, by integrating with respect to y, I get that c of y is the function, so the integral of 3y squared is just y cubed plus a constant d. And notice here, this is a real constant because I had an equation between functions of a single variable y, so when I integrate it, I don't have to fix any other variables before I integrate. I can just integrate straight away and get a usual, ordinary constant rather than a function of the fixed variables. So that's so we found our function, right? So the answer is really broken in 2 parts, but we did find our function. So let me put a square here around our answer. So our function is this. So 4/3 of x cubed plus 4x squared y plus c, but where c is this thing down here. So I was able to find my function, except that, well, I was able to find it up to an additive factor, but that's usual with derivatives. The equation that I gave you over here that I'm using to find the function f doesn't pin this function little f down exactly. It only pins it down up to a constant, right? This equation involves only the derivative of little f, so I can only find from this equation little f up to a constant, and I did exactly that over here. So there you go. This is how we can find the potential function of a conservative field. Now, So this is good. We're doing well. Next thing I would like to tell you is that all this works in 3D. So I'd like to write down, but there are quirks, so I'd like to look at the three-dimensional case with you now. So now let's look for the test for gradient vector fields in 3D. So again, but this time in 3D. Right, and the story is going to start the same. So we have a vector field f in 3 dimensions this time. So it has 3 components, and they're all functions of x, y, and z. So if this vector field is the gradient of a function of 3 variables, so this means this gradient has components f sub x, f sub y, and f sub z, then here's what I know. So I know, for example, that so we're going to have the thing we already knew before, right? We knew that f sub x is equal to f sub y, fxy is equal to fyx. So this is telling me, so let's see what this is telling me about the components of the original vector field. This is telling me, we've already seen this, right? So f sub x is p, so this is p sub y is equal to q sub x, because f sub y is q. Right, I'm saying that f sub x is p, f sub y is q. And then the first equation, the first equality between mixed partials tells me that p sub y is equal to q sub x. But in 3D, there are 2 other equalities between mixed partials. So the fact that you can take partials in any other gives me more information in 3D. So here's the more information we get. We get, for example, that if I take partials, I can take partials with respect to y and z in any order. So I know this is true. And I also know that I can take partials with respect to z and x in any order. Right. So let's now interpret all this in terms of, let's hide the function f and see what equalities I get between partials of the vector field, of the components of the vector field. So for example, here on the left, I have the z partial of f sub y is q, so that's first equation. Here on the left, I have the z partial of q. On the right of the same equation, I have the y partial of f sub z, that's the y partial of r. And now moving on to the third equation between mixed partials, I'm looking at the x partial of f sub z, that's the x partial of r, that is equal to the z partial of f sub x, which is the z partial of p. So you see, in 2D, if a vector field, if my vector field f was the gradient of some function, I knew that q sub x was equal to p sub y. But now in 3D, the components are intertwined more deeply. There are 3 relations that connect the partials of the various components. Right, I have 3 components and 3 relations between them. And so similarly to before, it turns out that these are all the relations I need to. So in good circumstances, these are all the relations I need to detect whether a vector field is a gradient field. So what I need here for this to be true is that the vector field is defined for all points in the plane. So what I just said. So let me just say this again. I just told you that if a vector field is a gradient of a function, then these three qualities between partials must hold. What I want to tell you next is that in good circumstances, if these 3 qualities between partials hold, then I can conclude that the vector field is the gradient of a function. So let's write that down. So this is a claim. I won't prove this now. I will give you. So I won't prove this claim completely, but we can definitely use it. But I will have a few things to say about this claim in the previous one, and it's 2D analog. So I'll say a few things about the 2D case when we have Green's theorem to work with, and much later in our class when we talk about Stokes' theorem, which is a three-dimensional version of Green's theorem, I'll be able to say something about the claim I'm going to write down right now. But here's without further ado, here's the statement. So if my vector field F, which has components P, Q, and R, right, functions of x, y, and z, is defined for all x, y, and z, so at all points in three-dimensional space, and I know that these three equations between partials hold. So that's saying p sub y is equal to q sub x, q sub z is equal to r sub y, and r sub x is equal to p sub z. Then the vector field is the gradient of a function for some function. For some function of three variables. Okay, so just the same as before, but this time we have three conditions rather than just the first one. So the method I showed you before that we use to find this potential function, this function whose gradient is my given vector field, that same method works in 3D as well. So so I encourage you to try the method for yourselves and looking at the lecture notes. So it's the same strategy as before, but this time with three variables. So basically, let me just say a few things about that. So here we'll have, so if I'm looking for, if I give you a vector field, I'll have really, if I'm looking for a function whose gradient is my given vector field, I'll have three equations rather than just two. And then I will do the exact same game, working one equation at a time. But I need to, but the point is that in order to use the first equation, for example, I will need to fix both y and z, and then integrate with respect to x. And as a result, at the end, I'll have a constant, quote unquote constant, that will depend on the two variables I fixed, y and z. And then I'll keep working with that. Anyway, please take a look at the lecture notes to see an example done out explicitly in 3D. Okay, so one more thing I'd like to say, and is that this theorem, this fact that if the conditions hold, if these equalities between partial hold, then for sure there is a function whose gradient is my given vector field. This only works when the vector field is defined for all points in the plane. So this first condition is absolutely essential. So in the notes I give you a vector field, an example in the supplementary notes. I give you an example where the equations between the partials does hold, but I also show you that the vector field is not the gradient of any function. And so this shows that you have to have the first condition there. Okay. So this is what I wanted to say about gradient fields. I'd like to move on and now tell you about Green's theorem. This is an amazing theorem. It looks very mysterious at first. So let's get to it. So now on to Green's theorem. Okay, Green's theorem. It's a formula that comes with a picture. So here is the picture. So I have a closed curve, and so that's I'll call this closed curve C, in the plane, and it encloses a region, a plane region D inside it, right? So C is, I'll just write everything here. Closed curve. And it has the quote-unquote positive orientation. So this is also important. I mean, this is kind of a... Let me just, write this and discuss this, come back to this later. So let me just leave it here. So with positive orientation, this just means that the curve goes in the counterclockwise sense, right? It's going like this rather than the other way around. And as I said, D is the region inside C. Okay, here's what Green's theorem tells us. It says that if I integrate, so it equates the integral of a vector field, p times dx plus q times dy. So it equates, it says that a line integral over this boundary curve C is the same as a double integral in the region inside of a certain derivative of these of the components here. So that's the combination of derivatives is q sub x minus p sub y. So let's look at this again. Let's look at all the various things. Okay, so let's look at what this formula is saying. So we're doing a double integral. So on the right, let's look at the right. So we're doing a double integral over this region D, and we're integrating a function of x and y. This function is the difference of it's a combination of these partials we've been working with throughout this lecture, right? So we're looking at the double integral of q sub x minus p sub y. So for a conservative field, q sub x minus p sub y would be 0, for example. Then the right-hand side would always be 0. But in general, it's not. Okay, so the theorem is telling me that if I integrate this funny derivative of the components, this combination of derivatives of the components p and q of the vector field I'm integrating, right? And this is a notation that kind of obscures the vector field. But if I integrate this combination of derivatives of p and q, then the result is is not something that takes place over the whole space. It's something that happens only on the boundary. It's a number. The result is a number that I compute just by going around the boundary of the surface and forgetting about the derivatives. So this is much like in the fundamental theorem of calculus, where for line integrals, where if I integrate a derivative along the curve, if I integrate a gradient along a curve, I can just forget about the curve and just evaluate the values of the function I'm differentiating at the two endpoints. So in the FTC, we go from a curve which is dimension 1 to a pair of boundary points which is dimension 0. Here we go from a 2D region which is dimension 2 to its boundary curve which is dimension 1. So you go down one dimension by going from here to here, right? You forget about one integral, and the price you pay is, well, you eliminate the derivatives. Let me make an important point here, and that is that so for this theorem to hold, there's one condition. Right here, we're doing the double integral of these partials over the interior of the function of this region D. So this means that so for the theorem to hold, I need that these partials, and in fact P and Q, are defined not only, so the left hand side is to compute the left-hand side, I only need to know P and Q on the boundary, right, curve. I don't need to know P and Q inside. But for the right-hand side, I need to know P and Q throughout the, I need to know at least this combination of partials throughout the interior of the region. So this theorem holds, so caveat, provided that P and Q are defined not just on the boundary curve of C, but on the inside of the region D. So caveat, P and Q must be defined throughout D. Right? Even though it seems I'm only using P and Q on the boundary, they actually need to be defined throughout the region D. All right, let me give you an example of Green's theorem and then return to the fine print of the theorem. So here's the example. Let's say we were doing a double integral over a disk of radius 3. Or rather, actually, we're interested in doing a single integral, over the boundary circle, over the circle of radius 3 around the origin, right? So this is radius 3. So the equation, you guys know it. X squared plus y squared equals 9. Okay, and we want to, and here I'm giving this circle the counterclockwise orientation, so I can apply Green's theorem. Now the integral over this circle I'm interested in doing is the integral of 3y minus e to the sine x times dx plus, and then the thing in front of dy, the function in front of the dy is 7x plus root of y to the fourth plus 1, okay, times dy. Okay, so it's a kind of a complicated looking integral. You see, not appetizing, not something we look, not something that I don't think many people are very excited about doing, but we're going to do this using Green's theorem. That's going to make our lives easier. So as usual, I'm going to call the first component P and the second component Q. Let's compute this integral using Green's theorem. Okay, so Green's theorem tells me that this integral, instead of computing it directly, we can compute it as the double integral over the disk, contained inside C, the disk with boundary C, of the x partial of Q. So in this case, so that's so the x partial of Q minus the y partial of P. All right, now let's compute these partials. So the x partial of Q in this case, so if I take the derivative of Q with respect to x, I'm just left with 7 plus 0, okay, minus now the y partial of P. The y partial of P in this case, so you see P starts with 3y, so the y partial is 3 minus, the second part has no y partial, so it's minus 3. So that's the final answer. So the thing I'm integrating here is 7 minus 3, which is just the constant function 4. And so, and now I ask you, what's the integral of 4 times dA over a disk? It's just 4 times the area of the disk, which we know is pi times the radius squared. So as a result, we get 36 pi. So we know the line integral without having to parameterize anything. We know that the line integral that this complicated looking line integral is just 36 times pi. I did it by pure algebra. I didn't have to really differentiate or integrate anything, which is pretty amazing. So this is a good example of how we'll use Green's theorem. It allows us to move from complicated line integrals to simple double integrals, or sometimes the double integral is a hard one, but the line integral is the easy one. So it just allows you to hop back and forth. Again, it's a computational tool. Right now we can just look at it as a computational tool that allows us to, whenever we're stuck with one side, we can compute the other side. And to emphasize, we're saying, the theorem is saying what happens when you integrate this derivative, and then you just get something, the values of the functions on the boundary. Okay, so a little bit about the fine print of the theorem. So I used a few words here kind of liberally. I talked about a closed curve with the positive orientation. So here's what that means. So what the word means, what the words mean. I mean, they're pretty much self-explanatory. For example, this curve over here is closed, and this over here is not closed. Right, so this is so a closed curve is, so the endpoints, it doesn't have endpoints. It's just a single, it's just a single I mean, you guys understand. It's something like a circle rather than a line segment. A curve that's not closed will have endpoints. Otherwise, it's called closed. Okay, and the other thing we need, the other thing in the theorem is the notion of positive orientation. So C, the curve C, let me move this to the next page. So the other thing I said is that the curve C is positively oriented. So C has positive orientation. So this means, so now I'm going to give you, so ordinarily this just means that the curve has the counterclockwise orientation. The closed curve has the counterclockwise orientation. I hope the mirroring of the webcam is not screwing up my, it's not messing with my orientation. But in any case, I mean this. So that's the ordinary situation. Now I'm going to give you the fail-proof criterion. So this just says, let me give you another way to say the same thing that's actually not, I'm sorry. Let me give you the actual definition, which boils down to being counterclockwise most of the time. So C has the positive orientation means that the region D, let me draw, okay, the region D is to the left of C. Because always okay, let's do an example. It's the best way to understand these things. So here's my curve C, and inside is my region D. So let me draw. Okay, so you see, if I go around C, if I'm a little bug going around C with this given orientation, the region is to my left. Right? So if I go around in the counterclockwise sense, in this case, you see that the region D will always be to my left. Now, the reason I didn't simply say counterclockwise is because some curves, so curves can have multiple components, right? I sometimes add curves, put two curves together, and then if a curve has two pieces, then So maybe the best way to think about a curve with two pieces here is to say that is to think that we start with the region D, and then then you can tell that its boundary curve has two pieces, right? Now the positive orientation for this boundary curve, if you follow this rule that the integral is that the so the inner loop actually, if I want the region to be to the right of the curve, the inner curves actually must have the clockwise orientation. Do you see? If I go this way, then the curve is to my left. But if I instead I was going to in the clockwise orientation, sorry, in the counterclockwise orientation for an inside curve, then the region would be to my right, which would be wrong. So in summary, I mean, basically, inner curves. So for outer curves, the usual case first. So for outer curves, we use the counterclockwise orientation. Clockwise orientation. And for inner curves, we just use the clockwise orientation, the other one. To conclude today's lecture, I'd like to show you how Green's theorem explains our criterion for gradient fields. So let's do this. So let's set the stage. So suppose we have our vector field F with components P and Q, which is defined at all points in the plane. And let's suppose, very importantly, that Q sub x is equal to P sub y. And let's suppose that C is a closed loop. Right? Let's show that in this situation, the vector field is conservative. Maybe I got ahead of myself. Let's show that with these two assumptions, so the first two assumptions, the vector field is conservative. To do this, let's check that the integral of f over any closed curve, any closed loop, is going to give me 0. That's our original definition of conservative. Okay, so let's look at the integral over C of f dot dr. So first thing to use, so we're going to use Green's theorem here. So first thing I'm going to do to this end is to shift to component notation. So our integral is written using vector notation, but I'm going to rewrite it using component notation. Right, so I write out the components for everything in the integral and do the dot product. So that's the integral over C of P times dx plus Q times dy. All right, now let's use Green's theorem. By Green's theorem, this is the double integral over the region inside C. So here's Green's theorem. Of the x partial of Q minus the y partial of P. Now by assumption, Q sub x minus P sub y is 0, by assumption number 2. And so this double integral is 0. So this tells me that that f is conservative, right? Green's theorem tells me that f is conservative under these assumptions. Right. So here I'm using what's important. It is important that when the first two assumptions are true for any closed loop, the integral will give me 0. I will get a 0 at the end. So this is pretty cool, and I didn't show you. So I didn't show you in class this in class, but it turns out, but I did mention it, that a conservative vector field is exactly the same as a gradient field. Right, so we did check using the fundamental theorem of calculus that gradient fields are conservative, and I never showed you this, but there is some information about this in the notes, and I'd be glad to discuss it during office hours, that the equivalence, the implication goes both ways, that a vector field is conservative if and only if it is a gradient field. So gradient implies conservative is easy, but conservative implies gradient is a little bit trickier, and I'm leaving that for the notes and office hours. It's the sort of thing I love to discuss with interested students. Okay, so this is what I had to say today. Thank you so much for listening, and I'll see you guys next time.